So in this video, we're going to continue practicing learning how to simplify trig expressions. And I really believe that when it comes to these concepts, that the more you experience, the more you watch someone else simplify and manipulate trig identities, you will gain the knowledge and experience on how you will be able to do it on your own. Now, let me just reiterate that these problems are not always going to be very intuitive on to know what to do when you see a problem like this, on what to do first. There is no steps that I can give to you as a guidance other than to give you tips on how I look at a trig expression and I notice things. In this particular lesson, I want to teach you to notice certain algebraic expressions and to utilize all the skills that you have learned from your algebra class to help guide you to helping you simplify. A lot of the fundamental identities will help you manipulate, but most of the skills that you need to simplify is actually your algebra skills that you've already learned in the past. All right, that being said, let's get started. All right, so for part A here, I notice first that this 1 minus tangent is being squared. So there's an exponent out here. And one of the most common mistakes students will do is when they see an exponent outside of parentheses, they'll distribute it inside, but you can't do that. The reason why is because there's a minus sign here. If there's a plus sign here or a minus sign, you can't distribute that exponent into the parentheses because that's not how it works. So this is not going to be 1 squared minus tangent squared. Okay, don't do that. Instead, what you need to do is understand that if something is being squared, or if there's an exponent of 2, that means it's multiplying itself twice. So what I would recommend is that you write the factor out twice and then multiply it together. In other words, let's FOIL. So if I were to FOIL, I need to multiply the 1 over to the first one, which is 1. 1 times negative tangent is negative 1 tangent, or negative tangent. Then if I take the negative tangent and multiply, that's negative tangent as well. And negative tangent times negative tangent is positive tangent squared. Basically, two negatives multiply make a positive. Tangent times tangent is tangent squared. And what we remember from last time is that whenever you're writing an exponent, you have to write it between the tangent or the trig word and the angle. So the exponent should always be in the middle. All right, now the first thing I notice is that the middle terms combine because they're both tangent to the first power. So if you treat this as negative 1 in front, negative 1 minus 1 is negative 2. So I'm going to bring down the 1 and then make this negative 2 tangent theta. So I have brought down the 1, combined these two, and I'm going to bring down the tangent squared. Now, one of the things I want to mention is that I can't combine this tangent with the tangent squared because they don't have the same exponent. It's just like me saying, like, I wouldn't want to combine, if I had something like 2x plus x squared, I can't combine these two because they don't have the same exponent. So they're not the identical x's. In this case, I think that's all I can do. The other thing that I do notice before I end this problem, I would say that I notice that this has a 1. This has a 1 and has a tangent squared. Anytime I have a 1 plus tangent squared, this is a Pythagorean theorem. So just as a reminder, one of the Pythagorean theorems, there are 3 Pythagorean theorems, but one of them says that if you have tangent squared plus 1, it's equal to secant squared. So the beauty of this is that if I combine these two, if I add 1 and tangent squared together, I get secant squared. So I can replace these two with secant squared, and I'll bring down the negative 2 tangent theta. Now at this point, I'm not going to combine any further. These are not like terms, so I'll just leave it here. I could probably do more, but at this point, I've already multiplied. I've simplified as much as I can. I think this is good enough. So I'll leave my answer at here. Now for this one here, I have cosine beta, b. This beta here is a Greek alphabet, and they're using it to represent the angle. So just think of it as another variable. And I have 1 plus tangent squared. So one of the things I first notice is that The cosine is outside. And yes, there's a parenthesis, so I could distribute this in. But the next thing I notice is I have a 1 plus tangent squared. Anytime I notice a tangent squared or sine squared or cosine squared or cotangent squared, anytime I notice a square, I always think Pythagorean theorem. Is there one of the 3 Pythagorean theorems that I can use to manipulate? And in this case, I already know that 1 plus tangent squared is going to equal secant squared. So I can replace all of this, whatever's in the parentheses, 1 plus tangent squared, as secant squared beta. And then I can bring down the cosine beta, and they're multiplying each other since they're sitting next to each other. And I could leave my answer like this, but I happen to notice that this is a secant and this is a cosine. And the beauty of secant is the reciprocal of cosine, so I think I could cancel something. So for secant, it's 1 over cosine beta. But what I notice is it's a square secant, so this should be a cosine squared beta. And then the cosine beta drops down, so I'm just bringing this cosine down. And I need to multiply these two. And because I noticed that this cosine, if I wrote it as a fraction, these cosines are diagonal from each other. So that means that I get to cancel out some cosine. So there's one cosine here, so I can cancel that one out. And if I cancel one cosine from here, I need to cancel out one from here. So that would leave me with one cosine left in the bottom. So this means I have 1 on the top, since this completely canceled. So I have a 1 in the numerator. 1 times cosine is just cosine in the bottom. And, well, okay, this is what I have left, but I know 1 over cosine is just secant. So my final answer would have to be secant. All right, so that was a nice problem to see that we can manipulate. We don't have to always distribute if we notice that the inside of the parentheses actually can be condensed more using one of the identities. So in this case, the Pythagorean identity really helped us out here. Now for this next problem, I noticed that we have 2 factors. So I'm thinking maybe I should FOIL because in this case, I have a sign here and a sign here. I can't really simplify the inside by anything. I can't combine anything or try to cancel out anything. So all I'm thinking right now is maybe let's try to FOIL. So if I FOIL, 5 times 5 is 25. 5 times 5 sine is 25 sine. And if I multiply the negative 5 sine, that'd be negative 25 sine. And negative 5 times positive 5 is negative 25 sine squared. So what I did was I multiplied the negative 5 with the positive 5, got the negative 25. Sine times sine is sine squared. So from here, I start to notice, okay, the middle terms are opposite signs, but they're both 25s and they're both sines. So they'll cancel each other since they're opposites. So the middle term cancel, which is kind of nice. That got rid of a lot of stuff. So 25 comes down and 25 sine squared comes down. And from here, I am thinking of leaving it, but then I noticed that they both have 25s, and I can do basically a factoring out. I can divide out 25 and put it in the front. So this is called factoring out. If I factor out 25, I have 1 minus sine squared. And let's just double check that I did this correct. So if I were to redistribute 25 in, 25 times 1 is 25. 25 times sine squared is 25 sine squared. Essentially what I did was I noticed both of them had a 25, so I divided out 25. So 25 divided by 25 is 1. 25 divided out by sine squared would just, make this a 1 in front, so I didn't write that. All right, so once I factored out the 25, I start to notice something. This inside here has a sine squared, and I'm thinking, maybe Pythagorean theorem, which has the one that is sine squared plus cosine squared equals 1. So this one's kind of close. If I move the sine over to the other side, that would leave me cosine squared 1 minus sine squared theta. And I want this to be 1 minus sine squared theta because I have that here. So what I did, I used the Pythagorean and I moved the sign over so I can say that it's 1 minus sine squared, and that is equivalent to cosine squared. So I can replace all of this with cosine squared, and I'm going to bring down the 25 that's next to it. And at this point here, I can't really simplify it any further. This would be my final answer. All right. So with this one here, I want us to notice something peculiar. Anytime you have a factor, right, and they look exactly the same, but they are opposite signs. So notice how these are opposite signs of each other. If you notice both of the factors are the same, but they're opposite signs, the middle terms will always cancel, which is kind of beautiful because in this case, all I really had to do was multiply the first number with the first number. So to get that 25, and the last number with the last number to get that negative 25 sine squared. So I really just had to multiply the front numbers and the last numbers. I really didn't have to FOIL all of it because the middle terms always cancel out when they're opposite sides of each other. So I hope you guys notice that and will utilize that in future problems. All right. Let's get into example 4. So example 4 asks us to look into factoring skills to help us simplify. And let's check out what they mean by looking into the first problem. So this problem here, I want you to notice that you have a cosine in both terms. So this is the first term and here's the second term, and they both have cosines. And the smallest cosine that we have here is cosine squared, whereas this one's kind of bigger, cosine to the 4th power. Now, this kind of reminds me of one of the warm-up problems in the first page. And let me show you that problem again. So in the first page, there was a problem where you had to factor, and notice how both of them had x's, right? The first term had an x and that one had an x, and you factored out the greatest common factor, which is x squared. And so that left behind y and x squared, so that when you redistribute, you would get back to the same scenario. So that's what we're going to be doing here, is we're going to be focusing on what trig function do they have the same, kind of like focusing that both of them had x's. In our case, they both have cosine. So since they both have cosine, I'm going to take out the smallest exponent, in this case, the square. So if I take out cosine squared, that means that this term only has sine squared left. And the other one would just have a cosine squared. Because if I were to redistribute cosine squared times cosine squared, it gives me cosine to the 4th power. Now when I do this, I notice something significant. Notice how this here is sine squared plus cosine squared. Anytime you have sine squared plus cosine squared, that's that Pythagorean theorem. When you ever have sine squared plus cosine squared, it's just equal to 1. And so I can say that this just equals 1. And if I bring down cosine squared, and if I multiply, this just gives me cosine squared. And that is going to be, I guess, it, because I can't really simplify that any further. For part B here, I have kind of the same scenario. I noticed that both of the terms have secant. So I'm going to try to do something similar and see if that works. And if it doesn't, no worries. I'll just go back to the drawing board and, try something else. So I'm going to grab out secant squared since it's the lowest power. If I do that, tangent squared is left in the first term. And this one here, if I grab out secant squared from this term, I need to also grab out secant squared from that one. So all I'm left with is a 1, right? Because secant squared times tangent squared is this here. Secant squared times 1 is secant squared. So that gets me back to my starting place if I want to. From here, I notice that I have a tangent squared plus 1, and that is actually a Pythagorean theorem. So the Pythagorean theorem says that tangent plus 1 is secant squared. So I can replace this with secant squared. And if that's the case, if I bring down my other secant squared, and since they're next to each other, I can multiply, it's implying multiplication, I'm just going to add up their exponents since they have the same base. So this is going to be secant to the 4th power, and from there I can't really simplify any further, so this is my final answer. So hopefully those factoring skills come in handy. So anytime you're noticing that you have multiple terms, but they have some of the same trig functions, maybe try this factoring skill where you factor out one of the, or factor out as the lowest exponent value. Now this one here, I want you to notice it has 3 terms. So it's a trinomial. And when I think about trinomials and I think about factoring, I go back to that warm-up problem where we're thinking about how we want to make our parentheses when we factor. Like this problem here is a trinomial, and this problem is actually very similar to the one we have below. So this one here, when we were factoring, we had to put down our x's, and we had to think about what numbers multiply to give us 1, but add to give us 2. And so there's only one set of factors that multiply to give us 1. It's 1 times 1. And then since all of these were plus signs, I knew that they had to have been pluses. So 1 times 1 gives us 1. 1 plus 1 gives us that 2x that's in the middle. So that's how I factor a trinomial. So if we take that skill to what we are working on, we can do something very similar. So for part C, I want you to notice we have cotangents, but I want you to think of them just like how you think of x's. I have a cotangent to the 4th power. So if I were to factor this, I'm going to need a cotangent on both. But then this one's special because it's to the 4th power. It's not a square. So in order to get to the 4th power, I need to make sure that both of them are squared. Because cotangent times cotangent gives me, adding up their exponents gives me to the 4th power. Now this here's a 1. So I know that the only things that multiply give me 1 is 1. So I know the numbers that go here is a 1. And since all of them are plus signs, this has to be a plus sign here. Now, if you're not sure that this is the factors that factor for this trinomial, then I highly recommend FOIL it out. So I'm going to just double check by foiling this out. You don't have to do this. I'm just showing to you that this does work. So if I multiply cotangent with cotangent, I would get cotangent to the 4th power because I'm just adding their exponent. Cotangent times 1 is positive cotangent. And then 1 times cotangent is positive cotangent. 1 times 1 is positive 1. I want you to notice that the middle terms are actually, like terms, so you can combine them. So this is a 1 and this is a 1, so this adds up to be 2 cotangent. Bring down the 1, bring down the cotangent to the 4th. From there, notice how this is exactly identical to this piece. So I know that this worked. So because this worked, I can go ahead and use these factors as my new factors, so I can try to manipulate this a little bit more. So going back to these problems, now that I am reassured that these are the factors, it does give me the same trinomial, I can try to manipulate. So I notice this is a cotangent squared, so I'm thinking maybe I can use the Pythagorean theorem. So the Pythagorean theorem that has a cotangent squared is cotangent squared plus 1 equals cosecant. So lucky for me, I have a plus 1 that's joined with the cotangent. So it says that cotangent squared plus 1 is cosecant. So I know that this is equivalent to cosecant squared. And since this one is the exact same, I know that this is cosecant theta. And so if I'm multiplying these two, all I do is add the exponents. So this is cosecant to the 4th power. And that is my simplified form. And I can't really simplify it any further, so I'll leave my answer here. All right, so for this next problem here, it gets a bit tricky. The first thing I notice is that the sign is squared, and I have a sign in the bottom. But unlike most problems where I can kind of split up the denominator with the numerator, this denominator is more complicated. It has a -3 with it, so I can't just try to split this up. So I'm thinking here, maybe I can try to factor this top, because now that I look at the top, it kind of reminds me of x squared minus 9. Yeah, you feeling me? So what I'm thinking is, like, if I treat this sign kind of like an x here, and if I'm thinking this correctly, and the bottom here is like an x minus 3, So I'm just kind of playing with my mind right now, and I'll come back to this problem. So like I know how to do a problem like this. If I factor the top, this would just be x minus 3, x plus 3. Because one of the things you learn in algebra is you learn something called the difference of squares. And what that means is anytime you have a quadratic or x squared, and this number here is a perfect square, but there's a minus sign in front, you can factor where they're opposite signs and they're the same numbers. Because the 9 is a perfect square root, 3 times 3 gives us 9. I know both of these need to be a 3. One of them needs to be a negative so that when I multiply, I get that negative 9. But because they're opposite signs, notice that the middle term isn't here. So if I do this, then I know that my bottom, which is a negative 3, can cancel. And that provokes me with some ideas. So what I'm thinking here, instead of me trying to like split up this, this denominator with the numerator, what I can do is just try to factor the top piece. So if I were to write this out, sine can be written as sine beta minus 3 and sine beta plus 3. Kind of like what I did over to the side here when I was just brainstorming. And so if I factor this, sine times sine gives me that sine squared. Negative 3 times positive 3 gives me that negative 9. So this works. And I know that the middle term won't exist because these are going to be opposite signs. Negative 3 plus positive 3 ends up being 0. Now at the bottom here, I'm going to just bring down as sine beta minus 3. And then I notice that these will cancel each other because the top and bottom are the same. And so this leaves me with sine beta plus 3. And I can't combine sine with a number. So this is my final answer. All right, so hopefully that brought in a new set of skills where we're looking at problems where there might be a difference of perfect squares. And it's a great one to try to factor, especially to try to cancel out something that's in the denominator, if you notice that they have the same factors. All right, so moving on to problem 5. This is where we get into addition and subtraction with fractions. And that can be quite difficult because we have to remember anytime you want to add or subtract fractions, you need a common denominator. And so we need to hone in onto some of those skills that we've learned in the past to help us out. Now let's start with something basic. So for part A here, I want you to notice that this has a cosine in the bottom and sine and cosine are in the top. So this goes back to some of the practice problems that we've done in the warm-up where we are looking at a problem maybe like part B, where when we were working out this problem, we noticed that the top had two terms, right? X and XY. So we can split the top into two fractions, but we use the denominator in both of the terms. So this denominator needs to go to the first term and the second term. And then we'll try to, split them up into two fractions and try to simplify from there. So we're going to do something very similar in the problem that we're given. So I want you to notice we have a cosine in the denominator. I'm going to split up the numerator. So this is going to look like sine theta over cosine theta plus cosine theta over cosine theta. So from here, once I split it up into two, I notice that cosine divided by cosine is just 1. Anything divided by itself is just 1. And then sine divided by cosine, well, if we think about it, the quotient that is equivalent to that is tangent. And I think this is it. Tangent plus 1, I can't combine them, so there's not much I can do here. And then at first I was like, oh, maybe I can use Pythagorean, but then I realized this is not a tangent squared, so I can't use Pythagorean. So this is really it. I can't really go any further. So I'm done. All right, let's practice that skill with part B. So part B is very similar. In this case, you have sine squared this time and cosine squared, but let's try to see if we can split that up into two. So I can write this as sine squared sine x cosine x minus cosine squared over sine x cosine x. So from here, I notice that there is a sine in the bottom and the top. So I can cancel out the sign in the bottom and cancel out one of the signs on the top. So all I'm left with is just sine on the top and cosine in the bottom. Now, the next part is I noticed that this is a cosine and there's a cosine in the bottom. So the cosine in the bottom cancels out completely, and I can cancel out one of the cosines in the top. So I really have cosine x over sine x. Now, before I leave my answer, I start to notice like, oh, I have a sine over cosine. That's just tangent again. And then this here is cosine over sine, which is basically the reciprocal. So if this is the reciprocal of this guy, then this must be cotangent. So if you look back at the quotient identity, this is definitely cotangent. And cotangent and tangent don't combine, so I can leave my answer like this. All right. In the next problem here, I have part C, and this looks like I couldn't do anything, right? Like I'm looking at this problem, it's like secant and cosine, these are not like terms I can't combine. But then when I really look into it, I'm like, oh wait, that's a secant. Secant is the reciprocal of cosine. I can manipulate this. Let's just try. So I can write secant as 1 over cosine because that's just the reciprocal identity that I'm using. And this one's just cosine theta. But the problem is this one's a fraction and I need to subtract from something that's not a fraction. But I can always force something to be a fraction if I put it over 1. But then I'm like, oh wait, they don't have the same denominator, so I can't really subtract. But then there's the argument if I want this to be a cosine in the bottom to match that denominator, I can just multiply the top and bottom by cosine. And so I'm like getting somewhere, right? And I bring down the 1 over cosine theta. And if I multiply the top and bottom, I get cosine squared for the top. And I get cosine for the bottom. And then from here, I start to notice, okay, I could now subtract the top together. So I could bring the top together now. 1 minus cosine squared. And I can write just one denominator. So I brought together the denominator since they're both common denominators. And this is where I start to notice something. I notice that there's a 1 minus cosine squared. And I remember the Pythagorean theorem. There is one Pythagorean theorem that says sine squared plus cosine squared equals 1. Well, if I were to subtract the cosine over, if I subtract the cosine over, this cancels, and I'm left with sine squared equals 1 minus cosine squared. And so 1 minus cosine squared is the exact same that I have here. So that means I can replace this guy with sine theta, or sine squared theta. So I can replace that with sine squared theta for my numerator. I still have a cosine in the denominator. But still, I'm not getting anywhere yet. I still have a sine and a cosine in the bottom. Sine and cosine top and bottom is tangent, but I have a sine squared on top, and this one's not a square on the bottom. So I have to be really sneaky here. So what I can do is I can separate the top and call this sine times sine, right? And then I'll give the cosine to maybe one of them. So I can't give it to the other one. If I gave it to the other one and said this, right? Then I would have cosine times cosine, which is cosine squared, and I don't have cosine squared. So I don't want to do that. So I'm going to get rid of that. So this is still the same value because sine times sine is sine squared, and then I have a cosine in the denominator. So everything's still the same, but the beauty of this is if I wrote it like this, sine over cosine is just tangent. So I've just changed this fraction into tangent, and I can move down the sine now. And so this looks a lot better. Looks like I have tangent times sine. All right, and I think this is it. Now at this point, before I get to the last problem, you're probably thinking at this point, it's like, oh my gosh, how do I know when to stop trying to simplify? And I'm going to tell you right now, it's really hard to tell. I mean, you can go on and on trying to simplify, but for me, I think you just keep going until you run out of ideas to try to simplify. That's my personal thought. Later on, I will give you problems where there is a point where you have to stop, but I'll introduce that in the next lesson. For now, what I want to expose you guys to is different ways you can manipulate a trig expression. So we're just practicing and noticing what ways we can manipulate something. So I want you to see all these combinations because I want you to be exposed to all the math that allows you to see all the different combinations you could do if you are in a pinch and you're stuck. So these are all different skills that help you problem solve when it comes to manipulating trig expressions. So for our last problem here, this one has two fractions and they don't have the same denominator because this one's a plus sign, this one's a negative sign. So if you were in Algebra 2, you might have learned something called rational functions and how to add them and subtract them. Some of you might have gotten to it, some of you might not due to COVID, but I will teach it to you from scratch. So if I were to analyze this problem here, what I have to do is try to get a common denominator. And to get a common denominator, I need to make them both the same. But when they're not the same, what I can do is treat them as factors. And if I want this one to look the same as that one, I can just multiply by the same factor. So I can multiply this side by 1 plus sine x. And I can multiply this side by 1 minus sine x. If I do that, then I have to multiply the top by the same factor. So the top also gets 1 minus sine x on this side. For this side, I need to multiply the top by 1 plus sine x. And so when I do this, now they both have the same denominators. Even though it's a very complex denominator, it's the same denominator. Now you're probably wondering, like, what the heck? Like, how did she know how to do that? Well, first off, let me give you a simpler example. So back in the day, well, when I mean back in the day, I mean like 3rd grade or 4th grade for you guys, when you had to add 1/2 with 1/3, okay? The simple idea. Well, your teacher probably taught you, well, you can explain this using finding a common denominator. And so you've learned that 2 and 3's common denominator can be 6. Right? So in this case, you can multiply this guy by 3 and this guy by 2. And so what you're doing is multiplying it by each other to help you find that common denominator, which is 6. And that is what we are doing here, is because I have a factor of something that is not identical, I'm going to take the opposite factor and multiply it with it so I can try to make the same factor. So now that both sides are the same, I'm going to move into the top piece. So the bottom is, or let me just do it in black. Bottom is going to be 1 minus sine x and 1 plus sine x. And this one here is also going to be 1 minus sine x and 1 plus sine x. And then for the top, if I multiplied this by 1, it's just itself, so 1 minus sine x and 1 plus sine x. All right, from here, since both denominators are now the same, I can join the top piece together and write this as one denominator. So I can write this as 1 minus sine x and 1 plus sine x. And the top, I would have 1 minus sine x. Oops, meant to write an x. Plus, so plus 1 plus sine x. Now from here, I notice that the numerator both have signs, but they're opposite sign. So this one's a negative sign, and that's a positive sign, so they'll cancel each other. So what I really have left is a 1 plus 1. So 1 plus 1 is 2. The next thing I notice is that the bottom here are opposite factors, right? This one's a negative and this one's a positive. So if I were to actually FOIL this out, I would just end up having, let's see, since they're already opposite signs, I know the middle term is going to cancel. So 1 times 1 is positive 1 plus, actually not a plus, minus sine squared x. So what I essentially did was just do 1 times 1, which is 1, sine, negative sine times positive sine is negative sine squared. Now from here, I thought I was done, but then I realized I have a 1 minus sine squared. And so in this scenario, when I have 1 minus sine squared, I actually have the Pythagorean Theorem for sine and cosine. So if I use the Pythagorean Theorem, you guys probably have heard of this several times, I can move over the sine by subtracting. So this is actually equal to cosine squared, because cosine squared is actually 1 minus sine squared. So I can replace this here, 1 minus sine squared, with cosine squared. So this is really 2 over cosine squared. But then I'm like, wait a minute, cosine squared is in the bottom, cosine's in the bottom. I'm thinking maybe this is secant, because secant is 1 over cosine, right? So if I were to write this as 2 times 1 over cosine, I start to realize I can replace this piece right here with secant squared. And I'll bring down the 2 so that it's multiplying next to it. And now this looks a lot cleaner. So I'll leave my answer like this. All right, that's it for this video. I know it was really long, but there's a lot of great practice problems here that I wanted to show you all the different skills you can use to help you identify what to manipulate to help you cancel out things and simplify the best that you can. All right, down below are some practice problems for you guys to try out if you would like to. I think it'd be a great way to expose yourself to new problems. I also want to mention that in the completed notes, I've actually worked out every single problem and show the work. I just want to let you know, like, if you want to check your answer or if you get stuck on a problem, that you can look at my example to help you figure out different ways to simplify the trig expression. All right, that's it for this video. I'll see you in the next. Bye, guys.